Now, so that's what we have, and there's a very nice consequence of this theorem, which I'll show you just a second. Okay, let me show you that consequence now, which is very nice. The remainder theorem. We also have what's called the factor theorem, and that's really what this says, as we'll get to. Namely, we know this is true. That's what the remainder theorem gives us. For x minus a to be a factor, okay, this means x minus a times something must equal to f of x. Okay, that's what it means to be a factor. It's just like with numbers, right? 2 is a factor of 10, right? Because if you do 10 divided by 2, you're not going to get a remainder. Well, you get a remainder of 0. So if x minus a were a factor here, then when you divide f of x by x minus a, you have to get remainder 0. So in other words here, the remainder, which is f of a, has to be 0. Again, let me say it again. If x minus a was a factor, okay, that means if you divide by x minus a, you have to get remainder 0. But the remainder is f of a. That's what we just showed. Okay? So f of a must be 0, is what we're saying. And the other way you can go around as well. Namely, let's suppose we knew the polynomial capital F. Let's say we know f of a has to be 0. Let's just say we know that. Well, then again, if you use the remainder theorem here, f of a 0, this piece is gone, and you're left with this. But what is this saying? This is saying x minus a times something is capital F. So x minus a is a factor of f. And that's really what we get here. Basically, we just verified the factor theorem, which is a consequence of the remainder theorem. Okay, so that's what happens here. All right. Now, so again, for the factor theorem, we have that a polynomial capital F of x has x minus a as a factor, if and only, so x minus a is a factor of f of x, if and only if f of a is 0. Okay? That's what happens here. So we have a much easier way to tell if x minus something is a factor of f. That's really nice. Okay, so that's good. Okay, so these are just some examples. For instance, let's suppose we have this polynomial. I mean, this you could factor easily. But first, let's wonder, is x plus 3 a factor of this? Well, I mean, by factoring, you would know yes. But we also know it's true because x plus 3 is x minus negative 3. And if you do f of negative 3, right, you would get 0. By direct calculation. So that's what's happening here. Okay? So that's what we get here. What about this one? What about, is x plus 3 a factor there? Well, if we were to evaluate this at x minus 3, at negative 3, right? X plus, remember, for this it has to be x minus a number. See? So in this case, f of negative 3 would be this, negative 3 squared minus 5 times negative 3 plus 6, which would be 30, which is not 0, so it's not a factor. So we have an easy way to tell if x plus 3 is a factor. I mean, you could actually just dive right in and divide it. You could also try factoring this, but we don't have to. We could do something even easier. We can do function evaluation. Any questions on this? Okay, let's keep going now. So here's another example that's good to do. Again, you could use polynomial long division, but really we don't have to. Synthetic is a little bit easier. Okay, so here's our polynomial. Now the first question is x minus 3 a factor of this polynomial? Is x minus 3 a factor? Well, again, by the factor theorem, we could check f of 3. Now, what is that equal to? Turns out it's equal to 0. That's what it looks like. It's equal to 0. Well, because it's equal to 0, we say, yeah, it is a factor. So we know that this is a factor. You know, it's kind of like with numbers, like 2. How do you know 2 is a factor of a number, of another whole number, right? You look at the last digit. Here we have a way to tell if x minus something is a factor of a polynomial. Okay, so we know it's a factor. Well, how do we get the other factors? Here's where you have to divide, and that's where I'm using synthetic division. Again, just think about the integers. If you want to get the other factors, you divide. Okay, so we're going to divide by x minus 3. Okay, so we put the 3 here in the first column, then the coefficient, one coefficient for each. Then we get a column for each remaining coefficient. So we have x cubed, we have 1. Negative x squared, that's negative 1, that goes here. Negative 14 goes here. Notice there's no missing terms, right? All the terms are accounted for. 24 goes in the last column. Okay, now let me get the red pen out. Remember, what do you do next? You bring this down like I did. Okay? Then you multiply, right? And whatever that product is, in this case it's 3. You put it up here, right? So that 3 goes up here. Then you're going to add negative 1 plus 3, and that gives you 2. That goes down here. So that's what we got here. Okay. And then the process repeats itself, right? You have negative 3, that goes down here to 2, which is 3 goes down to 2, right? 3 times 2, you get 6. The 6 goes here. Wait, let me say it again. 3 times 2, right? That's equal to 6. We put it up here. We add, we get negative 8. 3 times negative 8, that's negative 24, right? Put it here. So again, 3 times negative 8, right? That's negative 24, which is here. And now you add to get 0. So this, well, I mean, that's another way of confirming that, yeah, this is a factor. The remainder is 0. But now we know what the quotient is, right? This is degree 3. The quotient is degree 2. So we get x squared plus 2x minus 8. So this polynomial is x minus 3 times x squared plus 2x minus 8. Now, how would you get the remaining factors? Well, you would have to work with the quotient. Now, the quotient's not that bad because, you know, it's a trinomial, it's degree 2, so we could just factor it like we've seen before. You know, we can do that easily, right? Here, we want two numbers here, right? Whose product is negative 8 and whose sum is 2. So what's that going to do that? How about 4 and negative 2? Okay, so that works. So we get x plus 4 times x minus 2. And then once we know what this is, we can plug it in and factor this completely. Namely, we plug it in, we get x minus 3 times x plus 4 times x minus 2. Good. Any questions on that? Okay. Now, this example I'll say a little bit about, but really we'll do it next time using long division. Notice it looks like at first you cannot use synthetic division, right? And why is that? Well, synthetic division, you had to have x minus a number. But notice we have 5x plus 3, right? And we don't want 5x plus 3. Well, that is, we can't use synthetic division here. Okay, I mean, really, it's enough to check if this quotient has a remainder, because we're trying to see if 5x plus 3 is a factor of f. You know, that's what we're trying to see. Now, how can we use synthetic division? Well, we can convert the 5x plus 3 to x plus something. Namely, what I'm doing here is I'm dividing by 5. But whatever you do to the bottom, you have to do to the top to keep everything algebraically equivalent. And when you divide by 5, that's the same as multiplying by 5, which is what I'm doing. Now, if you wanted to, after all this, you're going to get this here, this quotient. And you could do synthetic division here, because now we have x plus 3/5. But I'm definitely not going to do synthetic division. I think it's just easier to use long division. Okay, so I will modify the notes, and I'm thinking next time we'll do this example. We'll do polynomial long division. Okay. All right, hold on, I'm not done yet, but let me just ask something. I asked this of the other class, so I want to ask it for everyone here. Oh, 9 people. Oh, well. Yeah, let me stop recording. Oh, great. All right.